Welcome to Spring LIB.
Hello everyone. Today we're doing chapter 18, problem 20, and this problem asks us to draw the products of the following reactions. So here we have some sort of substituted benzene ring reacting with a diatomic halide in the presence of a Lewis acid. Here we have the same monosubstituted benzene, but now reacting with a diatomic halide without any acid catalyst. And here we have some sort of benzene-derived substituent with also the diatomic halide and acid catalyst. So what we know about these type of reactions is that, well, they're going to be your electrophilic aromatic substitution reaction. That means that benzene is going to act as your nucleophile, and the Cl2 is going to be your electrophile. And what we know is that electron donating groups activate the ortho positions, and the para positions for attack on your electrophile. And in order to determine if something's electron donating or not, well, we need to look at the identity of the atom that's directly bounded to your benzene ring. So here we have oxygen, and carbon. So we know that oxygen with lone pair electrons and nitrogen with lone pair electrons are electron donating, as well as any R group or alkyl group such as carbon. So the reason for that is, well, if I draw a benzene ring here with this alcohol group, well, yes, oxygen is more electronegative than carbon, so you can say that there's going to be an inductive pull of electron density away from the benzene onto the oxygen nucleus. But something that outweighs this inductive pull of electron density out of benzene is the fact that oxygen has lone pair electrons, and it can form a resonance structure that makes a full negative charge inside your benzene ring. So through this resonance structure, we will get a benzene ring that now has a full negative charge in it. So because of this, this obviously makes the benzene ring a lot more electron rich and therefore more nucleophilic and more able to attack your electrophile. And now what happens when we have an electrophile with some sort of Lewis acid? Well, in this case, the addition of this Lewis acid can actually make this electrophile more electrophilic. So what I mean by that is now instead of just having chlorine, now we have chlorine, but it has a full positive charge on it. So because of that, you actually make this electrophile a lot stronger of electrophile. So now, because of that, when you do your electrophilic aromatic substitution, you'll make this bond, break this bond, and now you'll get one product that's going to be ortho substituted. But now you have your conjugate base, which is this. And because it's an acid catalyst reaction, you always need to reform your acid catalyst in your reaction. So in order to do that, and actually I skipped this step. So in order to do that, what you need to do is actually, you need to do two things. Well, number one, here we lost aromaticity. So you need to reform aromaticity, and in the process of that, you need to neutralize this carbocation. And then second thing is you need to reform your acid catalyst. Well, one thing you can do is that you can use these two electrons that's making this iron negative to pick up this hydrogen, making a bond. You make a bond, you break a bond, and now all of a sudden you reformed aromaticity. You reformed aromaticity. You formed HCl, and you reformed your acid catalyst. But now, because you reformed your acid catalyst, this process can go through multiple cycles, and what you can get is actually polysubstituted halogenation. So because with highly activated benzene rings, so in benzene ring that has OH or nitrogen, so a benzene ring that has OH or NH2, and when you react them with a catalyst, you will get a highly activated benzene ring. Therefore, you will get polyhalogenation occurring. So the overall product with this, with for A would be something that looks like this. You will have your electron donating alcohol, and then you'll have substitution at both your ortho positions and your one para position. So you'll have a tri-substituted halogenation reaction occurring for two reasons. Number one, you're reforming your catalyst so it can reactivate your electrophile to make it a better electrophile. And number two, you have a very strong nucleophile because the OH with the lone pair electrons on oxygen, or the NH2 with the lone pair electrons on nitrogen, are donating electron density to the ring, making a full negative charge inside your benzene ring, activating it for nucleophilic attack. So what you get is polyhalogenation, so you get a tri-substituted benzene like this. But now here, we have no acid catalyst. So here, you'll actually just get one of two products. You can either get your ortho substituted, like this, or you can get your para substituted product, like this. And now here we have now an R group. So R groups, they donate electron density through inductive stabilization, and the reason is because chlorine and hydrogens all have electron clouds around them. So those electron clouds can be shared with the benzene ring. So this makes the benzene ring a slightly better nucleophile than just benzene alone. However, it's a lot weaker than these derived benzene rings that could have a full negative charge inside the ring. So this is just a slightly better nucleophile than the benzene, while this is a lot stronger nucleophile than benzene alone. But then also we have this acid catalyst. So because we don't have such a strong nucleophile, it's as if we're reacting a highly activated benzene with this diatomic chlorine with no acid catalyst. It's the same thing as this one with no acid catalyst, but even though in problem C, we are adding this acid catalyst, and the reason we have to do this is because if we didn't, no reaction would occur because this electrophile is too weak and the nucleophile is too weak for any reaction to proceed. However, by the fact that this acid catalyst makes this electrophile a better electrophile or more electron poor, it allows this poor nucleophile to attack the electrophile so reaction can proceed. So you will get, once again, either your ortho substituted or your para substituted product, like this.